Good afternoon, everyone. Welcome to the second lecture on the week 8th. So basically, we have already covered the questions based on week 8th in the Tuesday. So today, what we are going to do, we will solve questions from the lecture, like from the entire course, and we'll solve some of the basics question. So I will just write the question and then we will solve it. So the first question is based on the bit error rate of BPSK. So in this lecture, we'll see the formula and the questions, and we won't go more into the technical description or the derivation of the formulas. So as we all know that the bit error rate is like in BPSK, the received symbol YK is equal to XK plus NK, and if XDK is equal to 1, if YK is greater than 0, means when the YK is greater than 0 at the receiver end, then it denote that the received symbol is 1. If it is 0, it denotes receive symbol is 0 when YK is negative, that is less than 0. So now let's suppose the transmitted symbol is 1. So the transmitted symbol is 1, so 1 means root under P and 0 means minus of root under P. So let's suppose the transmitted symbol is 0. Then Yk is equal to minus root P plus N. So for error to occur, Yk will be greater than 0. Then only it will say that it is the symbol received is 1, but actually the symbol transmitted is 0. So in this case, minus root P plus Nk should be greater than 0. Therefore, Nk is greater than under root of P. So the probability of noise greater than root P, that is given as Q function of square root of signal power by noise power. So this is equal to Q of square root of SNR. So this is the formula for bit error rate of BPSK, and also the signal is to noise ratio is P by sigma square. So bit error rate is Q function of square root of SNR. And when we have to find SNR in dB, so SNR in dB is equal to 10 log 10 into SNR. And there was one approximation that Q of like bit error rate is always less than or equal to half of e to the power of minus SNR by 2. So now let's take a question. What is the bit error rate of BPSK communication over an AWGN communication channel at SNR dB is given as 10 dB. So first we have to find the normal value of SNR when it is given in 10 dB. So SNR is given as 10 dB. So 10 log base 10 of SNR is equal to 10. So SNR is equal to 10 by 10, 10 to the power of 1. So this will become 10 only. So we all know that bit error rate is Q function of square root of SNR. So here it is equal to Q of root 10. So this value is equal to around 7 point, we can see in the Q table, into 10 to the power of minus 4. Now also the bit error rate of BPSK in relay channel. This is given as half 1 minus square root of SNR by 2 plus SNR. So this is already proved in the class. So for the same question, like let's suppose we have to find bit error rate of BPSK over a relay fading. So for this, we will substitute the value bit error rate relay fading is equal to half 1 minus SNR was 10, so 2 plus 10. So this will become half 1 minus square root of 10 by 12. So again, when you find this value, you will get 4.4 into 10 to the power of minus 2. And this bit error rate of relay can be simplified more. Like we can write this term as half 1 minus 1 by square root of 1 plus 2 by SNR. So this will be nearly equal to half 1 minus half of 2 by SNR. So this is nearly equal to half of SNR for larger value of SNR. And now today we will see also the concepts of free space propagation model. So the free space propagation model, today we will see the concepts and we'll solve question on this also. So this model predicts the received signal strength when there is an unobstructed propagation path between transmitter and receiver. So this means, let's suppose this is our base station. and so there is like unobstructed propagation path between the transmitter and receiver. So the free space equation that gives the received power as a function of distance d. So here the free space equation which gives the received power as a function of distance d. So in this case, the received power is Pt Gt Gr lambda square divided by 4 pi square d square L. So what is these terms? So the first term is Pt, that is the transmitted power transmitted by base station. The second term is Gt, that is the transmit antenna gain. And the third is Gr, that is receive antenna gain. And after that, lambda is the wavelength of the signal, and then lambda is equal to c by fc, also like speed of light by frequency of the, like fc is the carrier frequency. Now let's suppose we have to find this value in dB. Then we will do 10 log base 10 Pt Gt Gr lambda square by 4 pi square d square L. So this will become 10 log 10 Pt plus log Gt plus Gr plus 20 log lambda. Like we can find this using substituting the value, and then like this is the, in this way we can find the received power in the terms of dB. So now one more important concept is link budget analysis. So link budget of a wireless link is systematic listing of power losses and gains of different intermediate components in the transceiver chain. So it is basically, so this is the definition. So link budget of a wireless link is a systematic listing of power losses and gains of different intermediate components in the transceiver chain. So here there will be various additive and negative component. So we will see all these components first. So in the first column we will take all the components, then the symbol, and then whether it is additive or negative. So before that we will write the equation. So the transmit power given using link budget are as, so PT is the transmit power in dB, that is equal to SNR required minus GT plus the median link propagation loss L50, then MdB, that is the margin, minus receive antenna gain, then cabling loss due to the cables, plus noise plus interface loss. So this is the equation. Now when we write this equation for SNR required, then this term PTDB will go to the, then all this term in the right hand side will go to the left hand side and it will become in the opposite sign. So it will become PTDB plus GT in dB minus and then minus margin loss plus GR minus cabling loss minus noise plus interference power. So all these terms we will write one by one. So the symbol PT is our first is transmit power. So this is the addition of the power in SNR. So it is addition. The second is GT, that is transmit gain antenna. So this is also adding to the SNR. The third is, that is median link propagation loss. So this is like subtracting into the SNR. The next is margin. So margin also reducing the SNR. After that, that is mobile receive antenna gain. Then next is cabling loss. After that, that is noise plus interference power at the receiver. Then next is SNR required, that is on the our right hand side. So this is required SNR. So here this is the equation for the required SNR, and this is the equation for the transmit power. So we will take one question. So there is a wireless, like I will write only the main part. So wireless signal propagation scenario is there, where the cell radius D is given as 8 kilometer, carrier frequency FC is given as 2.1 gigahertz. Then transmit antenna height is given as 40 meter. Receive antenna height is given as 2 meter. Sigma is equal to 6 dB standard deviation for log normal shadowing. And to achieve reliability of 95%. Temperature T is given as 293 Kelvin. Bandwidth B is given as 30 kilohertz. Noise figure F. So there will be lots of values given in the link budget problem. So noise figure F is given as 5 dB. And then receive antenna gain is given as 5 dB. Cabling loss which is denoted by LC, is given as 3 dB, and transmit antenna gain is given as 12 dB. So these are the given things. So consider a scenario with level of interference equal to the noise power, and Rayleigh fading channel with average power unity through a link budget analysis. Compute transmit power required to achieve a bit error rate of 10 to the power of minus 4 at the receiver for BPSK modulation. So this is a very long question, so we'll solve one by one. So rho is given 95%, so that can be taken as 0.95. So that is the reliability. The median path loss is also given as 167 dB, and the margin loss is also given as 10 dB, and the noise power can be calculated as KTF. So K is 1.38 into 10 to the power minus 23. Temperature given is 293, and this F is the noise figure, that is 5 dB. So this is around 1.28 into 10 to the power of minus 20. So when we convert this into dB, we'll get as minus 154 dB. Now interference power is equal to the noise power it is given. So that is equal to 3.84 into 10 to the power of minus 16. So N plus I is equal to this value. So when we find this in dB, we'll get minus 151 dB. And bit error rate is equal to 10 to the power of minus 4 given. So this we have already studied, that it is 1 minus SNR by 2 plus SNR for Rayleigh fading. So we can calculate this value. So 1 minus 2 into 10 to the power of minus 4 is equal to square root of SNR by 2 plus SNR. So when you find this, it will be nearly 5 into 10 to the power of 3. So SNR in dB will be, sorry, from this value when you find SNR, you will get SNR is equal to 5 into 10 to the power of 3. So from this value, the SNR in dB, that is equal to 10 log 10, 5 into 10 to the power of 3. So that is equal to 37 dB. Now, so SNR is equal to PT. We'll use this formula. Plus GT minus L50 minus M plus receive antenna gain minus cabling loss minus N plus I. So all the values are in dB. So the finally SNR is calculated as 37 PT. GT is given in this question. So it will become minus 12 plus 167 plus 10 minus 5 plus 3 minus 151. Why we have taken minus symbol? Because these all are, let's suppose GT is positive when it is on the side of PT, but when it is in the opposite side of PT, then it becomes negative. So we have considered that. So it implies that PT will be, or we can take the same symbol here because PT is on this side. So now PT is equal to 37 minus 12 plus 167 plus 10 minus 5 plus 3 plus 151 dB. So the value of PT is around 49 dB watt. Consider the MIMO channel matrix H is equal to 1 2 minus 1 minus 1 2 3. The channel matrix is given as 1 2 minus 1 minus 1 2 3. So now we have to find the corresponding zero forcing receiver matrix. So FZF is the zero forcing receiver matrix that is given as H transpose H inverse into H transpose. Basically, you can write this when it is a real, like when the channel is having the real numbers, but when its complex channel is there, in that case it can be written as H Hermitian H inverse H of H Hermitian. So it's in the real case we will find like this. So H transpose is equal to 1 2 minus 1 minus 1 2 3, and this is also equal to finding the pseudo inverse. So now our H transpose into H, that is given as 6 minus 1 and then plus 4, that will be 3, minus 3 is 0, again minus 1 plus 4 minus 3 is 0, 1 plus 4 5 plus 9 14. So this is our H transpose H. Now H transpose H inverse is given as 1 by 84 60014. So this can be given as 1 by 14 1 by 6. Sorry, here this element got uh, exchange in the H inverse, so it will become 1 by 6 1 by 14. So now we have to find H transpose H inverse into HT. So this is basically our zero forcing matrix. So this will become 1 by 6 1 by 14 multiplied with what is H transpose, that is 1 2 minus 1 minus 1 2 and 3. So we will get 1 by 6, this is 1 by 3, this will be minus 1 by 6, again it will be minus 1 by 14, 1 by 7 and 3 by 14. So this is our zero forcing receiver matrix. So in this question this is only asking, so which is the correct answer? That is option number C, I guess. 1 by 6 1 by 3 minus 1 by 6 minus 1 by 14 1 by 7 and 3 by 14. So this option is the correct option. Actually this is option number D. So this is the correct answer. Now before moving to the next question, we'll see some theoretical concepts. Like bit error rate for BPSK pencil got discharged, so let's wait for a couple of minutes, then we'll again start solving the question. And also this video will be recorded and link will be shared in the NPTEL portal. So now we will see how the bit error rate for BPSK with zero forcing receiver can be found. So it is basically the bit error rate with receive antenna using maximal ratio combining what we have studied in the week 4th or 5th. Just we have to substitute L is equal to R minus T plus 1. So that is the, we have to substitute that L value. So bit error rate for BPSK with zero forcing ZF receiver is equal to just 2L minus 1 CL, the same formula what we have used for MRC. Here substitute L is equal to number of receive antenna minus number of transmit antenna plus 1. So what we will get? We will get 2r minus t plus 1 minus 1 c r minus t plus 1 1 by 2 of SNR to the power of L. So here L will be also r minus t plus 1. So let's consider a small example. Consider 3 cross 2 MIMO system whose SNR is equal to 25 dB using the ZF receiver. Find bit error rate. So we have just studied the formula of bit error rate. Same we will use as for the MRC. Only thing is we have to use L is equal to R minus T plus 1. So average bit error rate is equal to 2L minus 1 CL 1 by 2 SNR to the power of L. Here L is equal to R minus T plus 1. So what is R? 3 cross 2 receive antenna is there. So R is equal to 3, T is equal to 2. So our L is equal to 3 minus 2 plus 1. So it will become 2. So now we have to just substitute the value of L here is equal to 2. So average BER is equal to 3C2 1 by 2 SNR to the power of 2. So this will become 3 factorial by 2 factorial, that is 3 into 3 by 4 into 1 by SNR square. Now SNR is given in dB. So is equal to 25 dB. So we can find that in normal unit log 10 log 10 SNR is equal to 25. So SNR is equal to 10 to the power of 2.5. So SNR will be 316.2278. Our bit error rate is equal to 3 by 4 into 1 by 10 to the power of 2.5 squared, because it was 1 by SNR squared. So it will become 3 by 4 into 1 by 10 to the power of 5. So it will become 0.75 into 10 to the power of minus 5. This we can also write as 7.5 into 10 to the power of minus 6. So we can see in the when the number of antennas increases, the bit error rate decreased significantly. Now we will take a question. Now that is the last question for today's class. So consider a cellular system with n is equal to 48 channels per cell and blocking probability is 0.02, that is equal to 2%. The traffic per user is A naught is equal to 0.04 E. The cell radius is 1 kilometer as shown in figure. what is the number of users that can be supported in a city of 603 km square area? So in this question, so this is the figure, and the radius is 1 km, and the angle is 30 degree. We have to find what is the number of users that can be supported in a city of 603 km square. So here in this question it is given n is equal to 48 channels, and the blocking probability PB is given as 0.02. And we have to find the net offered load or supported traffic. So supported traffic A is equal to 0.04 into A naught. So A is equal to N into A naught. So N is equal to A is given 38.4 and A naught is given 0.02 is equal to 960. Now cell area is equal to 6 into 1 into, this is 1 kilometer, 1 by root 3. So this is the complete area of cell, that is 3.46 kilometer square. So number of cells is equal to city area, like total area of city divided by area of cell. So what is the city area? That is 603 kilometer square divided by 3.46 kilometer square. So the number of cells is equal to 174 cells. A number of users supported is equal to number of cells into number of users per cell. So number of cell is 174 and number of user per cell is 960. So the total is 167040. So there is 167040 users can be supported by the cellular service provider in the given city for the desired blocking probability of 2%. So this was one of the extra question. So today we will end the lecture here only, and this link will be provided and video will be uploaded on YouTube. So thank you everyone for attending today's lecture.